All right, this next section is all about simplifying, which means take an expression, in this case it's going to either have exponents or maybe radicals, and make it simpler for the reader. What does that mean? If it contains exponents, make them positive. If it contains a fraction, make that fraction as simple as possible. And if it contains a radical, please simplify that radical and make sure there are no radicals in the denominator. So let's make it happen. So looking at this first example, 6b squared, a to the negative third, all of that to the second power. The first thing I do is I would simplify the inside to 6b squared over a to the third power. And then all of that is going to be squared. And then, well, we know our properties, and we can apply that power of 2 to all of those individual components, and we're going to end up with 6 squared times b to the fourth all over a to the sixth. Well, 6 squared, that's just 36. I wouldn't say you have to evaluate these numbers all the time, but listen, 6 squared, that's easy enough. Go ahead and write that as 36. All right, in our next example, we got negative exponents galore. So what I suggest is start by simplifying what we've got inside of the parentheses. Let's simplify all that. And the way I like to do it is I know that if there's just multiplication going on in the numerator and denominator of our fraction, then I know anywhere I see a negative exponent, I can take this whole component, put it in the other part, so numerator to denominator, or denominator to numerator, and I can make that exponent positive. So I immediately know that we can rewrite this as, well, that b to the seventh can come up top, that a squared is now up top. Both of these guys, instead of having negative exponents, now have positive ones. And these two I'll put in the bottom with positive exponents. So we got this a to the sixth and b to the third, and don't forget our 5. All the negative second. And now I like to go ahead and simplify what we've got in here right away. There's some, I hate to use the C word, but some canceling that we can do. And I think we'll end up with a b to the fourth over 5a to the fourth. All of that to the negative second power. And now, well, I don't like raising things to the negative second power. I know that raising a fraction to the negative second power is the same thing as raising its reciprocal to the positive second power. And now we're going to go ahead and we're going to apply this exponent to every piece of what's inside of that parentheses. And we end up with 5 squared, which is 25, e to the 8th over b to the 8th. Fantastic. All right. Ooh, the square root of 3. I don't know what the square root of 3 is. The square root of 27. I don't know what the square root of 27 is, but I do know that since they're both square roots, we can write this as the square root of 3 times 27. What is 3 times 27? 3 times 27 is 81. And 81 has a very nice square root, namely 9. A lot more simplified to me. Awesome, let's proceed. Ooh, here we go. So we are going to treat this multiplication problem just like any we have before. So we're going to multiply 4 root 6 by 2 root 6, and then we're going to multiply it by 5 root 3. All right, so 4 root 6 times 2 root 6, what I think we should do is multiply the 4 and the 2, and we're going to also multiply the root 6 and the root 6. 4 times 2 is 8. The square root of 6 times the square root of 6, by definition, is 6. And now 4 times 5 root 3, well, we're going to multiply the 4 and the 5, and the square root of 6 and the square root of 3. 4 times 5 is 20. The square root of 6 times the square root of 3 is the square root of 18. So we're close to being done, but note that this square root of 18 we can definitely simplify. That's the square root of 9 times the square root of 2. So 3 times the square root of 2. So this all becomes 8 times 6 is 48, minus 20 times 3 square roots of 2. So 48 minus 60 square roots of 2. Let's check out number 30. Ooh, lots of fractions. Well, first things first, let's go ahead and simplify our coefficients here. Might as well. 18 over 3, also known as 6 over 1, so I'm just going to toss a 6 up here. All right, and now I know that, all right, I see the square root of 2, which I have no idea what that is. I see the square root of 72, I have no idea what that is, but since they're both square roots, I do know that we can write this as 6 times the square root of whatever their quotient is. Instead of doing the square roots first, like over here, we could find the quotient and then do the square root second. Is that going to be helpful? Absolutely. Why? Because 2 over 72 is the same thing as 1 over 36. Ooh, crazy. And the square root of 1 over 36 is just 1/6. And holy cow, 6 times 1/6 1. Who would have thought? Who would have thought at the beginning of this problem that this crazy complicated thing simplified to just 1? Awesome. All right, here we go. The negative square root of 80. Nothing really wrong with this, but in general, if we ever have a square root, a radical of any variety, we want to have as few things in it as possible, or a small number, please. So let's see if we can factor this into 2 other square roots, one of which is a perfect square. And I think this can factor as negative 1 times the square root of 16 times the square root of 5. The square root of 16 is 4, and so we end up with negative 4 square roots of 5. All right, making moves. Same idea here, the third root of 48, nothing wrong with that, but it's a root. We'd like to have as few things in it as possible. So let's see if we can rewrite that as the third root of something times the third root of something else, such that one of them actually is a perfect cube and simplifies nicely. So, how about the third root of 8 and the third root of 6? The third root of 8 is 2, and we end up with 2 third roots of 6. Booyah. All right, 33. So maybe we're thinking, oh, 50, that factors into 25 and 2, and 25 is a nice perfect square, but we cannot take the square root of a negative number, or at least it will not be real. So immediately, whoop, stop right there. Not real. Not going to happen. Don't need to do anything else. All right. Whew. Now we're trying to add 2 radical expressions together, but unfortunately their radicands are not the same right now. But maybe if we simplify them, maybe the radicands will be the same. They have the same index, they're both square roots, but the radicands are not the same, so we cannot add them yet. Well, let's see, 2 times the square root of 20, I think is the same as 2 times the square root of 4 times the square root of 5. And the square root of 45 is the square root of 9 times the square root of 5. Well, the square root of 4 is just 2. And the square root of 9 is just 3. Oh, check it out, so we end up with 4 square roots of 5 plus 9 square roots of 5, hot damn, for a grand total of 13 square roots of 5. I mean, that's a beautiful stuff right there. That's a beautiful stuff. All right, 35. All right, same idea. We've got a cube root, or a third root, and a third root, but our radicands are not the same. Hopefully, we can simplify to these, and maybe the radicands will be the same so we can add them. Let's see, so the third root of 54, I think we can write as the third root of 27 times the third root of 2. And the third root of 16, I think we can write as the third root of 8 times the third root of 2. And this is pretty sweet because the third root of 27 happens to be 3. And the third root of 8 happens to be 2. So we end up with 6 third roots of 2 plus 8 more third roots of 2 for a grand total of 14 third roots of 2. Okay, so here, at number 36, here we've got a irrational number in the denominator. We have a radical down there, the square root of 32, and we do not like that. It's just a little uncomfortable. It's not going to be so easy to work with. So let's help our reader by making that denominator a nice number. So what we need to do here is we're going to need to multiply by some square roots to somehow make it so that this square root in the denominator is a perfect square number. And so it simplifies to a nice rational, preferably integer. Well, I'm thinking of 32, and I'm thinking, well, it's not a perfect square. If it was, we'd be home free. Is there a multiple of the square root of 32 that is a perfect square? Well, let's see, 32, the next multiple is 64. Oh, hot damn! 64 is a perfect square. So if we can somehow get a square root of 64 here, we'd be home free. Well, what do we need to multiply the square root of 32 by in order to get the square root of 64? Just the square root of 2. And we end up with 8 times the square root of 2 over the square root of 64, but this simplifies, right? The square root of 64 is just 8. Got a little simplifying we can do here. These two guys simplify to 1, and we end up with just, whoa, hot damn, the square root of 2. Who would have thought that this simplifies to just the square root of 2? Okay, last one for this section. Same idea. We're going to need to multiply now by some sort of third root in order to obtain a perfect cube in the denominator. So let's think, multiples of 9 that are perfect cubes. 9, nope. 18, nope. 27, haha. 27 is a perfect cube. So if we can get a cube root of 27 there, with a third root of 27, we'll be home free. What must we multiply the third root of 9 by to get the third root of 27? The third root of 3. And of course, just like in last time, if you're going to multiply an expression by something, it's got to be 1. You can't change what this is, you can change what it looks like. So we multiply by 1 because it's the same numerator and denominator. Again, same numerator and denominator. So we end up with 15 times the third root of 3 over the third root of 27. But the third root of 27, that is a nice number. That is namely 3. We got some simplifying we can do. 15 over 3 is the same thing as 5 over 1. So we end up with just 5 times the third root of 3. Not so bad at all.